So in the last video we saw methylbenzene or toluene undergoing nitration, and the point of that was that it does it faster than plain old benzene and that it tends to give us ortho and para isomers but not much of the meta. Here's an example of the opposite situation. Here we have a CF3 or trifluoromethyl group that tends to react much slower than benzene, but look at the distribution of the products here. 91% meta and very little of ortho and para. Just the opposite of what's true with toluene. So again, there's other substituents besides methyl groups that lend themselves towards ortho and para, and CF3 here is just one of a number of substituents that lend themselves towards making a lot of the meta. So even though we've got three possible isomers that can be formed when we do reactions like these, again, the world tends to be divided into things that give you ortho and para versus things that give you meta. And CF3 certainly does that. So this is a good way perhaps to make that meta nitro isomer, assuming that's the position that you want that nitro group to go. Not a very good way if you're trying to make ortho or para. Here is the corresponding comparison of reaction rates at each of the 5 hydrogens that are available on that trifluoromethylbenzene compound. And so those numbers in blue tell us how much slower those positions are to react compared to benzene itself, where again we have the red number 1s there to compare. So notice all of those numbers in blue are on the order of 10 to the negative 6. So this is much slower than benzene itself. But they're not all equal to each other, and the two meta positions here, 67 times 10 to the negative 6, well, that is bigger than 4.5 times 10 to the negative 6. So that's why we do get more meta isomer compared to the other two. But yet compared to plain old benzene, if you're substituting on the trifluoromethyl ring, it's going to take more time and more patience to get substitution to happen at all. But when it does, you can expect to get a lot of the meta isomer. And on that chart on the very last slide of these chapter notes, you'll see CF3 towards the bottom there, because it is one of the slowest to react of substituted benzenes that have been studied. Well, what determines all of this business, whether something is more reactive than benzene or less reactive, whether it gives us ortho-para isomers or whether it gives us meta, all of that really comes down to understanding the carbocation intermediate that forms when you have something other than plain old benzene. Now this is the same slide that I showed earlier in this chapter that is depicting an electrophile adding to a plain benzene ring. But again, if you have something at the top instead of a plain old hydrogen right here, if that were a methyl group, then again this same reaction would be sped up. If that was a CF3 group, it would be slowed down. And it all has to do with the stability of the carbocation intermediate, because the effect of a substituent that's already on the ring definitely has an effect on how stable that carbocation is. Remember, with carbocations, the faster, the more stable they are, the faster they form. And so it's all about the stability of that intermediate. If you can get this carbocation to form, then the final step of forming your ultimate product is pretty fast and easy. This is the real hurdle here. So we're going to talk a little bit about, in the next slide, some scenarios of having certain substituents already on the ring and what that means for the stability of the carbocations that you can form.